Okay, I'm back. Sorry. So I want to encourage you to pause the video right now and to read this this little blurb here that I've had written, just so that you can process it or attempt to process it on your own first, and then I'm going to talk you through it as well. So in 4.4 part 3, when we were talking about the second fundamental theorem of calculus, we talked about treating the definite integral as a function, an accumulation function, to be more specific, sorry. So in this case, where whatever capital F of X is being evaluated at, that's what gets plugged in here. And then you end up evaluating F of T on the interval from A to whatever X is, right? So that ends up being capital F of X, or F of whatever the number is that you've plugged in, minus capital F of A. That's how we can treat the definite integral as a function. Where F of A, in this case, would be equal to the integral from A to A. And you guys know that that would be equal to 0. But what if you know, or you're given in the problem, that F of A is equal to something else? Like, what if you are given a function value for capital F, or whatever the antiderivative of the function that you're integrating is? So let's say that you know that capital F of A is equal to C, where C is not equal to 0. And you want to determine what F of B is, but you know from our previous discussion that the integral from A to B of F of T would represent the net change of capital F on the interval from A to B. Where if you integrate from A to A, you get 0, not C, right? So F of, in this case, right, F of A would be equal to 0 and not C, because I'm telling you that you are given that F of A is equal to C, where C cannot be equal to 0. So we had some problems. We had a couple problems, I think, where we ran into this issue. We didn't think about setting up the integral as a function, as its own function, but we did. But we had to take into account like a starting value. The one that first comes to mind was the coffee, right? So at t equals to 0, we were given that the coffee was 90 degrees. So we had to take into account that starting temperature and then add the net change. So we need to make sure that we are taking into account what F of A is, as long as it's not equal to 0. If it's equal to 0, it doesn't matter, right? Because F, in this case, right, integrating from A to A would be just 0. And that's fine. Or you would end up doing 0 plus whatever definite integral represents your net change. So when we are trying to write what we call an accumulation function, it's in this form where you need to take into account the given information and treat whatever the given information is as your starting point. So F of A, and then the lower limit of integration here should match, right? So this value for this function should be for this x value. And so that we're taking into account a starting point. In other words, we can think of the accumulation function as the amount I have now equals the amount that I started with plus the amount I've accumulated since I started. Okay, so this is a past FRQ that we're going to take a look at. It is calculator active, so I have my calculator handy, and we're going to work through it. So it looks like we are given a table here. It says the temperature of water in a tub at time t is modeled by a strictly increasing twice differentiable function w, where w of t is measured in degrees Fahrenheit and t is measured in minutes. At time t equals to 0, the temperature of the water is 55 degrees Fahrenheit. Okay. And that's reflected in the table. The water is heated for 30 minutes beginning at time t equals to 0. Okay. Values of W of t are at selected times t for the first 20 minutes are given in the table above. Okay, so use the data in the table to evaluate the definite integral from 0 to 20 of W prime of t. Using correct units, interpret the meaning of that definite integral in the context of this problem. Okay, well, W prime would be the rate at which the temperature in degrees Fahrenheit is changing with respect to time in minutes. So when we integrate from 0 to 20, that means that that's going to end up being equal, if we think about our fundamental theorem of calculus, so 0 to 20, W prime of t dt would be equal to, oh, sorry, that was 20, W of 20 minus W of 0, which is the temperature at 20 minutes minus the temperature at 0 minutes. So it's going to tell us what the change in the temperature was over those first 20 minutes. And we can see that W of 20 is 71 degrees Fahrenheit, should include the F, minus 55 degrees Fahrenheit. So 71 minus 55 is 16 degrees Fahrenheit. We need to make sure that we interpret the meaning. So we have correct units, but we need to interpret the meaning in the context of this problem. So we can say that the temperature of the water, we got a positive value for our net change. That means that the temperature of the water increased by 16 degrees Fahrenheit from t equals 0 minutes to t equals to 20 minutes, or you could say like over the first 20 minutes. The temperature of the water, to be even more specific, you could say like the temperature of water in the tub, just to make sure that, yeah, you are really answering in the context of the problem. Okay, and then question D. So we did part B of this previous free response, and we're doing part D. The other parts, maybe we don't know how to do yet, or do not relate to what we're talking about right now. Okay, so for t between 20 and 25 minutes, The function W that models the water temperature has first derivative given by W prime of t equals to 0.4 root t cosine of 0.06 t. Based on this model, what is the temperature of the water at T equals to 25? So we want to figure out what W of 25 is. We want to know the temperature in degrees Fahrenheit at T equals to 25 minutes. Okay. Well, we know what the temperature was at 20 minutes. So we could use that as our starting point. So we could say that's equal to W of 20, which is 71 degrees Fahrenheit. And then we want to know what the change in the temperature is from 20 to 25 minutes. So we could integrate from 20 to 25 W prime of T. And this is a calculator active question, so we can type this into our calculator. So in your calculator, you're going to type in 71 plus the definite integral from 20 to 25 of 0.4 times the square root of t. In your calculator, you'll type in x. Okay. You can just type in, since everything is assigned though, you can just type in or write down this statement. And then we are going based on the model, what is the temperature? Okay. So then typing that in. Make sure you are in radians. So I get approximately 73.043 degrees Fahrenheit. So the temperature of the water at T equals 25 minutes is approximately 73.043 degrees Fahrenheit. Okay. So one was just calculating the net change in temperature. The other, we were actually finding a temperature at a specific time. Okay. And another calculator active problem. This one about raw sewage. Lovely. Here, we'll use brown. Raw sewage is leaking from a storage tank at a rate given by the equation S of t equals to negative e to the square root of t, where S is measured in gallons per hour. Okay, so S is our rate, and T is measured in hours. If at T equals to 2 hours, there were 572 gallons of raw sewage in the tank. And then we're going to answer these questions. Okay. How much sewage has leaked out of the tank from T equals 2 hours to 5 hours? Okay, so we want to know how much sewage has leaked out. All right. So that means we want to calculate the net change in gallons of sewage from 2 to 5 hours. So we are going to integrate s of t. And you do not know how to integrate that yet, so you're going to type it into your calculator, and we'll get an approximation. And some of these, a lot of times the calculator active ones are just so complicated, like you wouldn't be able to integrate them by hand, or it would just take a zillion years to figure out how to. Okay, so we get approximately negative 19.723 gallons. Okay, so that means that, okay, how do I want to word this? From t equals 2 hours to t equals 5 hours, approximately 19.723 gallons of sewage have leaked out of the tank. Okay, how much sewage was initially in the tank when it started leaking at t equals to 0 hours? Okay, well, in that case, we would want to figure out what the net change was Okay, so we would still want to set this up as, what do I want the amount of raw? We'll use R to represent the amount of raw sewage. So like we're trying to figure out what R of 0 would be. We know what the R of 2 is, right? So R of 2 is 572 gallons. And then we are going to integrate from 2 to 0. From 2 to 0, because we want to know what R of 0 would be. Right? If we were setting this up as in terms of T, this would be R of T, right? And this would be T or X, right? R of X. So we want to plug in 0 there. Okay, so then that's 572 plus that integral. And if we want to switch it to be from 0, you don't have to, but from 0 to 2, right? You could make that minus, and then it would cancel with that negative. U root T dt. And typing that into the calculator, since we are calculator active. Oops. All right, I got approximately 577.408 gallons of raw sewage. So there was approximately 577.408 gallons of raw sewage in the tank at T equals 0 hours. Write an integral equation that gives the amount of raw sewage in the tank. Oh, A of T. I should have looked ahead. Let's change this to be A. I already kind of talked us through this, right? So A of T will be equal to A of 2 plus the integral from, or let's say A of T. Okay. 2T I guess we should technically maybe change that to be an X. Just so that those variables are different. I guess if you're replacing T, I guess that's okay. It's just that we're not plugging whatever T is in right away. Here, I'm going to use X. That should be an X. So I'm going to let A of T equal to A of X. Okay, and that'll give us the amount of raw sewage in the tank at time T, or time X.